From one perspective, my perspective, knowledge graphs and their schemas are really made to make things easier, namely data sharing, data discovery, data integration, and data reuse. So knowledge graphs belong, in my opinion, in the realm of data management and in the realm of, well, the rather long and probably often not quite as prominently perceived as it should be area of research where you try to make data management easier. The motivation for this type of research and development is, well, if you look, for example, at people who do data analytics, and of course, data analytics in particular, using all kinds of machine learning techniques, deep learning techniques these days is a very hip subject as opposed to data management. But if you talk with people doing data analytics, then they tell you, and there have been studies on this, that they often spend a big proportion, kind of 80% of their time actually searching for data, integrating data, curating data before they actually can use it for the stuff they call data analytics. So 80% of the time they're doing data management. And the big cost factor here is the data management piece. And that hasn't really changed over the past decade. And so research into how to lower this cost factor is, well, as important as ever, or even more important, perhaps, given the ever rising abundance of data which we have. Okay, so, but let me go to knowledge graphs and we'll go there step by step. And I want to give this here a try because rather than showing you my slides, I want to do a live demo, which is always risky, but in this case, it's not my own program, it's actually Google search. So if you go on Google and give in a well-known entity, sorry. And I'm in Kansas now, so I know Laura Kelly is the governor of Kansas, which I did not know before I moved here. Then for a few years now, you do not only get responses in terms of links to websites where this string appears, but you also get on the right-hand side what Google calls an info box. And this info box contains structured data about the entity, in this case, Laura Kelly. And what this gives us, in essence, is a glimpse into some of what Google calls the Google Knowledge Graph, and which it has launched prominently several years ago. Now, why is it a graph? Well, there's relationships down here. You can think of them as edges with edge labels, like, for example, an education link to another entity. And if we click on this, then we make a hop in the knowledge graph, namely to the Indiana University School of Public Health, Bloomington. Let's do that. And we see we get the standard Google search responses on the left, and on the right-hand side, we get the next info box. So we just traverse to a different node in the knowledge graph. And then, for example, there is a Dean link here going to David B. Ellison. And again, we can take a hop. Now we're at David B. Ellison's page, etc. So much for the live demo. When I just tried this out briefly before the talk, I noticed that this is now different than when I did this on the slides. The slides were created quite some time ago, well, these pieces of the slides, but I think there was no difference there a few months ago when I last looked at this live. It looked like this, that Laura Kelly has education, but given was Indiana University rather than the Pacific School. And then from there, I used the has president link to Michael McRobbie. So yeah, these knowledge graphs change. And of course, while you can see this as a graph, there's a node here, a node here, a node here, and two edges between those nodes given there. That doesn't necessarily mean that the way this is represented in the background, in the system, in the graph, which Google doesn't share with us because they share with us only the few things they show publicly, that the representation structure there is exactly the same. It most likely isn't. But anyway, it gives us an idea why this would be a graph, or could be understood to be a graph. So if we put this now as a graph, then we could, for example, extract something like this. Laura Kelly has education at Indiana University, has President Michael McRobbie, has education University of Queensland. There's a birth date, there's a number of students, things like this. And what I want to drive at here is that whenever you have a graph like this, which presents information in this type of graphical structure, then in fact there is always an underlying schema. The schema may not always be available or sometimes not even explicitly written down, but somebody decided on the structure of the knowledge graph, on the names of the relations, right? And thought about how do these things connect to each other, because if you do it yourself, there's a lot of choices how to do that. So at least there is a schema in the an underlying schema in the head of the person who actually constructed knowledge graph, whether that person consciously thought about it or not. So for example, this would be a schema we could consider as perhaps underlying what we just saw. And now I replace the specific entities with type labels or class names, as we sometimes call them in our field. So there would be a person, that Laura Kelly was there. Also down here would be another person, which was the president of Indiana University, an organization. And then there's also data types like date, number, for example, has birthday links, has student links, etc., etc. So now, one of the things we're looking at with emphasis in our lab and also in other places is, what is a good schema? What does it actually mean to have a good schema? And remember back kind of what I gave as the main motivation for looking at knowledge graphs the first time. What is a good schema to make data integration, reuse, discovery, sharing easier? Easier in terms of, well, for example, if you share and somebody else discovers your knowledge graph based on your schema, how do we make it easier for that person to understand what's in the graph and how to integrate it with other data and then reuse it for whatever purpose they see fit? Because that is the 80% of work, or part of the 80% of work in data management, before you can actually do something interesting with data. Okay, so we had that already. Now, when Google came up with this, they of course didn't come up with this out of nowhere, although the name they chose, namely knowledge graph, hasn't really been used for a long time, and certainly not in this specific context. So the name knowledge graph, or the term knowledge graph, I think in that modern sense can really be traced back here to Google using it. But the principle around that, namely using these type of graphs and underlying schemas, is something which is much older. And to just give 2 pointers, they are standards by the World Wide Web Consortium, which were recommended, which were actually, these are the second editions here, which you see 2014, 2012. First editions were 2004. The first one, RDF, actually also had a version 1999. And of course, there was stuff they were building on. So this is not new. But essentially, the thing on the left, the resource description framework, or RDF standard, is a standard for describing knowledge graphs primarily, with also some light typing at least. And on the right-hand side, the web ontology language can be understood as a language for describing knowledge graph schemas in such a way that they are compatible with RDF. There's other approaches for doing that, but this is kind of one of the traditional ways of doing this. Let me give you a brief idea what these are about. So what is RDF in a nutshell? Well, there's different syntaxes out there. I'll show you one which is called turtle syntax. And things would roughly look like the lines here. So the first line, Laura Kelly has education at Indiana University, is pretty much that piece of the knowledge graph. Laura Kelly has education at Indiana University. And then Laura Kelly has birth date, and there is a date here, which of course I did not put in the exact right syntax to make things a little bit simpler. But that would be another part of the knowledge graph, and so on. Now you notice the strange columns. That's because one of the things you do here is you describe everything using URIs. Essentially, syntactically, the stuff you also put into a web browser. You want to find a web page at the top. Not URLs, not necessarily, because they do not have to resolve to a specific web page, although they usually do if you kind of did it nicely and well understandable for other people. Starting with a colon essentially just means that you start with some default namespace, whatever that may be, google.com or something like this. And these edge node pieces are called triples. A knowledge graph in that sense is essentially just a set of triples. And I mentioned already, this syntax is called RDF turtle syntax. And this standard also prescribes a serialization XML. That's actually the most important. So again, you can layer this in XML, which is a little bit weird because XML is really made for representing graphs, but it's just a serialization such that you can use standard tools for dealing with this stuff. So that's RDF in a nutshell. And the community I'm primarily associated with, which is the Semantic Web community, which has produced these standards, has been putting out knowledge graphs under a different name for, well, a long time. I think it earnestly started around 2008, 2009. And one of my colleagues, Christopher Janowicz from University of Santa Barbara, in 2012, did something I found very interesting. He just went out on the web, crawled the web for RDF data, for linked data. That's what it was called back then. And essentially threw away most of it. He only kept the pieces which had geo-coordinates attached to it. So a longitude and a latitude value. And whenever he found such a pair, he put a dot on an empty screen. And what came out was the picture shown here. So there is no underlying map. It's just the dots coming from the longitude, latitude coordinates. And I used this picture to show just what in 2012, which was before Google launched the knowledge graph, how much data was already out there, right? So, okay, so there is a lot of data out there, all kinds of different domains. Okay, now from RDF, which is for expressing the graph, let me just go a step towards OWL, which is an ontology language. And you can really often use ontology very interchangeably with the term knowledge graph schema. And I will do so. For our purposes, they're pretty much the same thing. And let me just tell you in a nutshell what OWL is about, the web ontology language, which is the other standard I mentioned earlier. The web ontology language essentially is a type language. It allows you to express complex relationships between types. So classes is what they call there. So they are the types like person, organization, etc. Then you have the relations, which are called properties. And the relations are the edge labels. So it has birth rate, has education, these kind of things. And then the exact relationships between these terms, which you want to use in your schema, are recorded using a formal logic. So for example, you could encode the statement, every university has a president, which if you speak first order predicate logic would look a little bit like the formula at the bottom. There's usually a different syntax used for these, but let's not go into these details. So you can use this type of logical expressions, not full first order predicate logic, it's more restricted, to express these complex relationships which inform your schema and inform the graph structure for the knowledge graph you may want to do. So if you want to look logic, if you're not that much into logic, just ignore me for 2 minutes. Class is essentially a unary predicates, relations are binary predicates. You have and or negation implication, some restricted use of quantifiers for all and exists. And then you can specify subclass relationships between classes or, well, more complex classes, which you can also construct, or subproperty relationships like has mother is a subproperty of has parent. We can talk about domains and ranges of properties, etc. When we do modeling, so we model with a lot of domain experts in different areas. I'll mention a few things a bit later in the talk. Then one of the things we are developing, have developed mostly in the past few years, is a modeling process for making good schemas, in whatever sense good, we'll talk about this. And when we do that, then it's usually a team effort. So with domain experts, and our whole process is also made such that we don't have to make the domain experts also experts on ontology modeling or on logic or something like this. We actually mostly use schema diagrams to facilitate team modeling, and you'll see a little bit of that later when I go into concrete examples. Okay, so for example, we have worked with some ocean science data repositories, large-scale repositories like the Bicodemo repository at Woods Hole, or the R2R repository at Columbia University, or the Data One repository at NCs in Santa Barbara, to help integrate data from different repositories to make a joint search hub. That was a project that was finished a few years ago. Like that was, for example, one of the things we did. Rather interesting. So, I knew nothing about oceanography before that. It's always interesting because I kind of learn while doing that. But again, our process is also made such that if I'm the modeler, working with domain experts, I don't have to become an expert on whatever the topic is. So it's really just teamwork we're doing there. Another project we're currently doing together, well, it's driven by people at Michigan State University at Matrix. So historians, who are historians in the historic slave trade. And the project funded by the Mellon Foundation is about, well, something rather similar. You make a hub about data about historic slavery with focus on the US, but not only. And again, what we're doing with them, or our part of the project, is that we actually developed a schema which they use to warehouse and to integrate their data. Okay, so schema. What's the problem with schemas? Can't everybody do a schema? And kind of what's the problem with ontology modeling as well? Kind of, you probably know that 15 years ago, it was kind of very hip to do ontology modeling with OWL, and lots of people did it. And the result is that most of the, and I really say most, if not almost all, of the ontologies out there which you can grab from the web are what I would consider of very, very doubtable quality. And one of the ways this shows is, for example, that if we need a knowledge graph schema, then we find that it is usually much less work to make one from scratch than reuse what's out there. Because they're just kind of, yeah, weird, tricky, wrong, have bugs, don't really work, but there's other reasons and I'll come to them. So let me give you a glimpse of the problems you may run into when just naively doing some of this modeling. So for example, what I've shown you earlier, the kind of the little schema I extracted from the example, that is, or actually it's not the schema, that's the knowledge graph itself. This is actually not a good knowledge graph for a lot of purposes. And this is also why I think that this is not how Google actually has it in the background. They're just not telling us how they do it. This is a simplified view on their data, which they provide. So why do I say it's not a good knowledge graph? Well, the problem is, as soon as you think of not one specific short-lived application, right, or one short-lived research project, but you think long-term, meaning you want data which others can use, which you can reuse, which you can easily modify in the future, etc., then you'll find that this doesn't work here because, for example, this is only a very specific time slice. Presidents of universities change. Now, how would you, in this schema, say since when Michael McRobbie is president of Indiana University? Right? The schema doesn't provide for this. So this knowledge graph doesn't provide for this. So something's not quite working here. Or a little bit more problematic, number of students. Let's make a different example. Say you have a city or a metro area. You talk about number of people living there. Well, it's obvious that this is actually probably a matter of not only the week, but the day and probably also the hour at which you count. But even more problematically, nobody counts. Nobody does that. Well, there is a census, of course, but a census in the end, you know, is never perfect either. And for the years between the census, and in other countries you don't have this frequently anyway, you don't count people as often as you do in the US. And in the time in between, what do? You use statistical models. So the number which may be listed for a certain year, for example, on one side may be different from the one on the other side because it depends on the statistical model. So in order to do something which really looks at populations in a fine-grained way, well, for some applications, it may be important to know where did this data come from? Where do you have it from? And what is it based on? What statistics is it based on, etc. Now, all this information cannot really be put in here. Okay, so that's why I'm saying this is not a good knowledge graph. I mean, not even in the very simple sense, right? Like when was Michael McRobbie president seems to be just something you want to know if you don't look at data only from a very specific time slice. Okay, so what makes a good data model? And that's a very tricky question, but of course one which interests us very much. So we're kind of constantly revising this as well, but just a few things which in our experience are important. A good data model, so a good schema, or a good knowledge graph organization, if you want to put it that way, resonates with both human expert conceptualizations and with data and use case requirements. So of course you have to look at the data you have, because that's important. But then you also have to talk with the human experts or the use case experts to understand what is actually needed. And if you look too specific at just one use case, then yeah, you may get a good schema for that use case, but you're not going to make your data model easily reusable. You need to look at a kind of larger scale of use case. And what helps in this case is really interact with the human experts and think about how do they conceptualize their world? How do they think about it? And can you capture how they make the terms rather than let it driven from let's say pure data or pure database perspectives? Can we capture the human element in the way we organize knowledge graph? And if you do that, then one thing follows almost automatically. Namely, if you organize your data in such a way that it reflects human expert conceptualizations, then it seems rather evident that that also makes the knowledge graph easier to understand by a new person who was not part of the modeling process. And that is part of what we're trying to do. Okay, generally low maintenance costs. So you want to have a sustainable model in the sense that it is robust for future use and reuse, and also that it's extendable without high management cost. You want to make it easier to integrate it with other data or to modify it, things like this. And then of course you want to kind of adhere to standards such as readily available software and tools work, etc., and other things like stakeholder buy-in, etc. But let's not focus on those. That's actually not primarily what we're looking at. So one lead question for our research in this area is, how do you lower knowledge graph management costs while meeting requirements? And kind of we follow a couple of principles, like we're trying to bridge interdisciplinary barriers. The model has to make sense both for the data experts and for the domain experts who may actually not be so concerned in how you represent things in a computer. So we want to resonate with human expert understanding, and of course follow leading standards. Okay, so knowledge graph schema modeling. How do we get at that? It helps to try to start understand why existing ontologies are so hard to understand and to reuse. And again, this is based primarily on our experience here. One obvious thing is poor ad hoc modeling. If you model ad hoc, then using it by somebody else is often just outright not what you should be doing, because it's not going to fit the purpose. Another problem, even if well designed, ontologies are sometimes very large monolithic entities. So kind of it's a lot of classes and relationships and logical axioms, but they're kind of one big thingy, and you don't really understand what's going on because you kind of can't make sense of it because there's just too many trees there, which means you can't really see what the forest is about. So the problem here is primarily monolithic. That's not the way how humans conceptualize an area, right? Of course, they understand this network, but they can also tell you about the key notions and the key aspects of the key notions and things like that. So representing this kind of structure within the schema is one of the things we'd like to do. One of the problems with reuse is also that you may have different use case requirements on granularity in different parts of the model. Some parts of the model may be too fine grade, others too coarse, too much from a bird's eye's perspective. You see that in all ontologies almost necessarily, because there's always a core concern which you model in detail, and the more you go to the, say, fringe, if you want to put it that, of the model, the coarser it becomes. Now the problem is with reusing is that you may have a slightly different focus. So you get this monolithic thing and you don't even know where to start to modify it because you don't know kind of where the conceptual pieces are. Okay, so one of the things I'm accelerating here a little bit, so I'll skip quite a few slides, but I put a download link for the slides in the chat, in case you want to look at the pieces which I can't talk about it in that much detail. So one of the key things we're doing here, and this is a departure from traditional ontology modeling, is that we think of modules within an ontology. So rather than thinking of an ontology primarily as an enhanced taxonomy with additional links in it, which is a traditional way of looking at ontologies, we think of an ontology as a set of interrelated and possibly overlapping modules. And each of these modules is essentially a part of the ontology which represents a complex concept in such a way in which it resonates with the human expert. Okay, so it's these different pieces, key terms, which we model and which get interconnected to make an ontology. And that's really a big difference. And why I say it's a big difference, for example, look at, if you're familiar with ontologies or if you're not, but you're looking at all kinds of tools you can find for ontology modeling, then you'll see that they all really support this kind of monolithic big thingy. And they're often very driven by taxonomy and then enrich it. But it's just not the way we think about a domain area. Okay, now, and together with this, we make principled use of what some people call ontology design patterns. An ontology design pattern is essentially a solution template for a recurring problem in ontology modeling. Like, for example, in a lot of applications where you want to make such a knowledge graph schema, you need to talk about trajectories, things that move over time, right? So that seems to be a recurring ontology modeling problem. So is it possible to make a general pattern for modeling this, which you can reuse or adapt for your different purposes? And the answer is yes, you can. And that is one of the ideas here. You don't kind of need to invent everything from scratch, but if there's good patterns for a lot of things which occur a lot, then you're not making a naive model in this case, but you're reusing something people have put a lot of thought into already. So this is another main idea we do. So what do? We usually have a modeling team, right? We have domain experts, data experts, ontology engineers. We use a divide and conquer approach. We first decide on the set of modules to be modeled, or a first set of modules, and draft modules one at a time. And then we kind of glue them together. And that's not how it's traditionally done. That's how we do it. And we also work mainly through schema diagrams in natural language, through domain and data experts, with really the goal that the ontology engineers don't have to become domain experts, and the domain experts don't have to become ontology engineers, and they shouldn't. It's not what they primarily do. Okay, so we have a concrete set of steps. The number changes because we change that in granularity often as well, but essentially it follows these things here. Defining a use case, making competency questions, identifying key notions, which become modules then in step 4. And then the rest is essentially what ontology engineers do to make the model out of that. But the first 4 are really the kind of interesting thing I want to focus on. And let me run through a few examples for patterns, and then very quickly talk about how we do this for, well, in our recipes tutorial. So here, for example, in the top would be a generic agent role pattern. So the idea here is that you don't have a university which has president agent, person, because of the reasons mentioned earlier. Kind of, this is the role a person takes for the university, and that role may be, for example, temporally dependent. So when that role is taken, maybe central. So what you do is, when you talk about the role of an agent, then the something, in that case, the organization, university, provides a role, which may be the president role, performed by an agent, and then you can attach to this piece here whatever context information may be important. Like, for example, that there's a start and end time for it, for example. Another generic pattern, which we call a stub pattern, is shown in the middle. Now, it's a stub because it's not a real pattern. It's a simplistic pattern, a so-called stub, but it's still helpful in some cases, in particular at the fringes of the ontology, where you do not yet want to go into fine granularity. Now, what you can do is, for example, you can join these two patterns together. That's shown at the bottom. Right? So you take different patterns, join them, and then you can specialize this if you want to your specific purpose. Like, for example, say you talk about movies, I want to make an ontology about movies, then the thing here would become movie having an actor being an actor role, okay, assumed by a person having a name, for example. So this gives you an idea how to get from patterns as templates to modules, right? The actor role module would be here. Okay, some other patterns which we like to use. This is from an ontology called the QDT ontology, which is rather nice. It talks about quantities and units. And I don't want to go into too many details how this is done here, but it's a really nice pattern. They also have a controlled vocabulary for quantity kinds like length and mass and things like that, and for the units, which makes it very nice to use. Another pattern we really like, again, this is stolen from an ontology, a standard, a W3C standard, namely the Provenance ontology, Provo. And again, I don't want to go into details for the sake of time, but this is a rather powerful little model, little pattern, which as a pattern, we can just reuse or adopt in a lot of cases. Yeah, provenance, data provenance is important, and hard to find a case where it isn't important, actually. Okay, so I talked about stubs already, so let's leave that. But now let's move in the last 10 minutes I have, just very quickly in how you would go at modeling recipes using our approach. And this is a glimpse only, of course. We've all written up versions. At the end of the slides is lots of references if you want to go into details. Oh yeah, that is actually where you currently find it. There's a new version coming out this year, I believe, on this. Okay, first step, define use case or scope of use cases. So before you go into modeling, you need to know what you want to do. And here, if you want to model something in a way such that it's reusable by others more easily than usual, you would not only look at a very tiny use case, but at the scope of use cases, or probably include in your use case what may happen in the future. Like you may develop the system, or what the system may want to look like after extension in 5 or 10 years. And that gives you a much better idea how to model it in such a way that it remains extendable. So here would be a problem setting, a use case description. I'll read it. Design an ontology which can be used as part of a recipe discovery website. The ontology shall be set up such that content from existing recipe websites can in principle be mapped to it. The ontology gets populated with data from recipe websites. On the discovery website, detailed graph queries using the ontology shall produce links to recipes from different recipe websites as results. The ontology should be extendable toward incorporation of additional external data. That's now the scope of use cases. For example, nutritional information about ingredients or detailed information about cooking equipment, etc. So this gives you a rough description of what you want to do. I'm not going to discuss whether this is something one would really want to do, right? Or how tricky that would be regarding copyright stuff, etc. This was a tutorial, right? So it's a thought experiment from that perspective. Part 2 now. So now we have defined the use case. Now what we do is we find or make competency questions. Ideally, you ask users kind of, what would you like to have searchable on such a hub? And of course, you also look at possible data sources. You try to scope the problem, like what do you want to model now? What do you want to do later? Let me give you an example for competency questions. So for example, how do I make a low-carb pot roast? How to make a sweet breakfast under 100 calories? How do I prepare chicken thighs in a slow cooker? You know, I mean, you can think of all kind of difficult stuff as well, or kind of breakfast dishes which can be prepared quickly with 2 potatoes, an egg, and some flour. Oh, there is an FL missing here, because that's what I just happen to have in the fridge, right? For example. That's not how I usually do the cooking. I just see what I have in the fridge and try to make something up, but that may be just me. So in any case, you get these competency questions. For the Enslaved project, which I mentioned earlier, the historians actually went out to lots of people, including schools, general public, also scholars, and, compiled big lists of competency questions to understand what actually should be modeled, where should the emphasis be. Now, once we have the data, the use case, and the competency questions, we identify in the next step key notions which should be modeled. And they really become the modules then later, or that's where we start. This usually gets revised as you start going. So for example, in our scenario, we could now extract from what we just discussed. Well, recipe seems to be a key notion, quite obviously. Food, time, equipment, food classification, kind of side or dessert, difficulty level, nutritional information. Provenance is important because you want to give reference to the websites we got it from. So that may be a list and perhaps something to look at in roughly this order. That may be something one may want to do. So we prioritize this list, and then we look at identifying key patterns which we know already about. Of course, you need to know what patterns are around. We made a design pattern, ontology design pattern library. For this, there's also ontologydesignpatterns.org as a website with lots of patterns of very varying quality, I would say, because it's more just like everybody can post there. So for example, recipe, what is it? And now you think of, when you do this, you think of what pattern should I use? Should I use a pattern for document, or a pattern for sequence, or a pattern for process, or a pattern for plan and description? And here I need to make a decision, right? And sometimes it's obvious, sometimes it isn't. And then I need to look at the use cases, discuss with the domain experts, etc. It seemed to us here naively, a recipe is really a plan. It's a description. And that's primarily because for the use case we're looking at, we're not so interested in the process details, the steps. We're really interested in the overall plan, particularly in what goes in, what comes out, kind of thing. Okay. Food. For food, for example, when we think about this now, we come across questions like, do you mean a concrete piece of food or an abstract quantity? The 100 grams of cucumber I have in my fridge, or an abstract 100 grams of cucumber, etc. And then we can go through this list and identify patterns if they exist. They may not yet exist, so we may have to model from scratch. But for some, we can use something which has been done before. So for example, here would be at the top something you could call a pattern for a plan, going from initial situation to a goal, which is also a situation, having a plan description. And now once we say a recipe for our purposes is a plan, we can just use this and use it as a template for what you want to do. The recipe is the plan. It produces a situation and requires a situation which has constituents, primarily in our context, which are quantities of food, probably also cooking equipment, stuff like that. And there may be cooking instructions down here, which are the recipe instructions, which, well, for our purpose, looking at the use case, is probably not something we really want to model, fine-grained. But yeah, they could be here and it could be extended. So abstract quantity of food, well, we take our quantities and units pattern, which I showed earlier, instantiated from quantity of stuff to quantity of food, and having a food type here. Talk about stubs. I'm kind of moving a little bit quickly here now. And for provenance, yeah, we can use the provo pattern, but that's too complicated for our purposes because we really only want to say it was derived from a previous website, and then talk about who the person was or what exactly the activity was which was generated, which is sometimes important for provenance. But we can still use this and simplify it by only taking the pieces we want, and we would still have this pattern. So let me just add one more thing before I wrap this up. I know I have only 2 minutes. Use of patterns here serves a lot of purposes. It serves, one of the purposes is that you don't make an overly simplistic model. It also serves the purpose that we can actually keep information like which pattern did it come from. We make that part of the ontology we build. We also make the modular structure part of the ontology we build. And that essentially means we can display it using our tools, which we're building for this purpose, to whoever wants to use it to make sense of the conceptual pieces rather than this big monolithic ontology, and to understand where they come from and what these pieces mean, to also make them easier to exchange with other ones. So for example, if we identify where the provenance module is in our ontology, then if ours is too simplistic, they could just replace this module with a more complex one if they wanted to. But if I have a big monolithic ontology, then I cannot really do this, okay? Because I do not know where the module is because it was only in the head of the person modeling. Okay, so you may want to do something from scratch, like nutrition fact labels, stuff like that. And then we have all the kind of final steps, which have to do with putting it into a logic, circling it back, of course, to the main experts, checking whether everything is okay, etc. But the key thing really, and let me skip a few things here, is that after, and we work with these schema diagrams, really, the ontology modelers have in their minds that we need axioms in the end, but we don't want to show that to the domain experts. Even on the diagram level, we can then in the end take these little pieces of diagrams, the modules, and join them together and get a diagram for the whole ontology. And for the ontologies engineers in the room and the notes they took during the discussion process about the exact relationships between the notions, that means that essentially they can now make the axiomatization out of that. Perhaps ask a few more natural language questions to the experts if something's missing. Okay, so this is roughly how we do this. And as last slide here, one of the things we're currently developing is a set of compatible tools as plugins to the very well-known ontology Protégé editor. And you can find it at commodity.com. Commodity is what we call the system. We're also developing corresponding ontology design pattern libraries. Again, the slides are posted. Okay. Let me just, thanks a lot. Let me answer to one question which Bill asked. Sounds like software engineering with the concept of refactoring and metrics. Yes, indeed. One of the motivations here is to look at the notion of software design patterns and have an analogon in the ontology world. Of course, they're very different, but still, yes, it's idea, make kind of structured models out of it. So that's the right way of thinking about it. Thank you very much, and I'll stop here.
Thank you very much, Pascal, for your enlightening keynote. Once again, can we have some applause in the background there? And now, ladies and gentlemen, I think it's the second half of the paper session where we have two papers in the program. So the first paper is entitled Hierarchical Clustering of World Cuisines. And the lead author and the presenting author is Krit Sharma from Delhi Technological University in India. I believe we have Krit as part of our attendees. Do we not?
Yes, yes, sir. I'm here.
Okay, all right. Okay, so welcome, and please feel free to share your screen and to start your presentation.
Yes, sir. Just see. Yeah. So is this visible?
Yes, we can see. Thank you.
Okay. So good afternoon, everyone. I'm going to present the paper Hierarchical Clustering of World Cuisines based on the research conducted by me and my fellow interns at the Center for Computational Biology under the mentorship of Dr. Ganesh Bagla. So, so as we all know, cooking began with the invention of fire. And since then, humans have evolved, and it is inevitable that the cooking practices evolve too, even though it may happen inadvertently. Although the principles of cooking remain the same, different practices have emerged in different regions, leading to the development of varied cuisines. Hence, each cuisine now has acquired a signature style. The purpose of this work is to probe interrelationships among cuisines for developing insight into human behavior and cultures as a means for shaping the future of the food. So how do we do that? So we aim to create a hierarchical tree of all the cuisines of the world, and this is done and then follow this purpose. So for this, we have divided the goal into three parts. The first is cuisine fingerprinting. So it refers to characterizing the unique features that typify every cuisine. These features are then used to create a tree, and the relation between the cuisines is obtained via this tree. Thus, we can identify similarities and differences between these cuisines, and this can be referred to as the food ontology part of this work. So after this is done, we can create or we can identify interesting patterns into the between food and the culture of the humans. So for our research, recipe DB dataset was used as the data source. It contains more than 118,000 structured recipes spanning over 26 cuisines. The dataset provides the nutritional information along with the ingredient processes, utensils, and some other useful information regarding every recipe. This has also been told by my colleagues earlier, Devansh and Tushar. So for this work, we used only the major factors like the ingredient processes and utensils to identify patterns from these raw data. So pattern mining was done using FP growth algorithm, which is a faster implementation of Apriori algorithm. These algorithms are widely used in data mining applications like the market basket analysis and data security. So to explain further, I would like to tell you about the Apriori algorithm. So Apriori algorithm is based on generating candidate patterns from the given items and pruning out the infrequent ones. For example, consider the image on the left hand side. Here we have 5 items A, B, C, D, and E, with this we can create all the combinations that you see. And as we move down this tree, the combination tree, so we can see or we can receive supersets of the previous ones that are the item sets that are in the previous layer. So this is the candidate generation part, and FP growth, however, skips this candidate generation and achieves a higher speed than the Apriori algorithm. So hence it is faster than the predecessor, and the rest of the process is same in both the algorithms. So many combinations are generated, and we have to prune out the infrequent ones as they do not contribute anything interesting. So therefore for this pruning, we use the fact that if an item set is infrequent, then all its supersets must also be infrequent. And you can see in the right hand side image that the item set AB, when found infrequent, all of its supersets have also been pruned out. So but how do we identify if an item set is infrequent or not? For this a new term called minimum support threshold has been defined. So traditionally it refers to the minimum number of times an item or an item set should appear in the total transactions. However, here these transactions translate to the recipes that are present in a cuisine, and the items refer to the ingredients, processes, and utensils of the recipes. And we have also set the minimum threshold to 0.2, which is the 20% of all the recipes in a given cuisine. So here you can see some of the patterns that we have obtained, and along with these patterns, they in the upper table you can see the corresponding support and the region in which they have been mined out, and also the number of patterns that we have obtained in each of these regions. These are some of the cuisines that we have obtained, and the complete table is present in the research paper, so you can refer to that too. Furthermore, we have provided Thai examples of Thai and USA cuisines here. So please note that the patterns are not only combinations of ingredient or process or the utensil. So the combinations that we have generated here combine all of the three substructures. For example, in the US cuisines, the patterns that we have identified the pattern boil, bake, and preheat. So although I'm not a cook, I can say that this is an essential step which is important for creating any baking food. And the fact that the pattern is frequent in US cuisines we can say that in US cuisines there are a number of recipes involving baking. Hence, these patterns also provide us information about the frequent practices used in a cuisine. Another example would be that of the Indian subcontinent cuisine-based pattern. So the pattern onion plus add plus heat plus salt. So this is an essential step in a famous Indian practice called tadka. So thus we can say that these patterns help us in fingerprinting the cuisines. For some other examples relating to the patterns that we have mined out, you can refer to the GitHub link presented here. Once these patterns have been mined, we can create the tree. For creating the hierarchical tree, two approaches have been proposed. One is frequent pattern-based clustering, and the other is authenticity-based clustering. So, as the name suggests, frequent pattern-based clustering uses the frequent patterns that we have mined earlier, and these are fed to the hierarchical clustering as features. But these patterns are simply strings and are not computable. So these have to be processed before being fed to the hierarchical agglomerative clustering module. So therefore, all these patterns are first appended in a unique set, and across all the 26 regions. And the set now contains only the unique patterns that we have mined across all these regions, and each string now can be treated as a separate category. Thus, this facilitates a label encoding, and now we can create we can transform these patterns into a computable form. So these string patterns now form the feature vector for each cuisine, and have been fed to the hierarchical agglomerative clustering or HAC module. Different distance functions have also been used, like the Euclidean, cosine, and Jacquard distances for the same. Authenticity-based clustering. It is based on the notion that some items have a positive relationship with the cuisine, while some have a negative one. And this fact can be used to identify characteristics of every cuisine. For this, first we have to create a prevalence matrix, which is created using the equations that you can see here. This is the first equation, and this is the second one. So in the first equation, we calculate the prevalence of each item I in cuisine C, which is the ratio of NIC to NC, where NIC is the total number of recipes in cuisine C where item I has occurred, while NC refers to the total number of recipes within the data set. Using this, we identify the relative prevalence of each of the item in a cuisine, and this is calculated using the difference of the prevalence of the item I from the equation 1 and the average of all these and the average of the prevalence of item I across all the cuisines except the cuisine C. So once this is done, we can say that the prevalence matrix has been created, and now we select only the top 10 and bottom 10 items prevalent in each of the cuisine. This leads to a unique set of 263 items, and these 263 items are then used to characterize the cuisine, all the cuisines. So our matrix of 263 by 26 dimension is created and is fed to the correlation module, and we have used Pearson correlation for this work. And once the correlations have been obtained, we can create the hierarchical tree. So moving on to the results section, since there is no validation metric to describe how the tree should actually look like, so we used the geographical distance based tree shown here. And this is because geography is an important factor in deciding the vegetation, and hence it indirectly affects cooking. Furthermore, the metric is also easy to implement, and the tree was created using the centroids of each region, which were identified using their latitudes and longitudes, and finally fed to the hierarchical agglomerative processing module. And this is the result that we have obtained for this, and is used for validating the ones that I'm going to show now. So these are the results that we have obtained using the frequent pattern based clustering. On the left hand side is the HAC with the cosine distance, and on the right hand side is the HAC with Euclidean distance. So as you can see in both of them, the Chinese and Mongolian, as well as the Japanese, Thai, and other Southeast Asian cuisines have a close relationship to one another. Similarly, the cuisines in the European region like Dutch, UK, Belgian, Scandinavian, and French have also shown a closer relationship to one another. Thus, this shows that the tree follows the geographical proximity relationship. However, there are some anomalous patterns that we have obtained, which we will be discussing later. And this is the result that we have obtained for the authenticity-based clustering. And here also, a similar relationship is obtained between the Southeast Asian cuisines as well as the European cuisines. So, however, a relationship between a negative relationship between Indian subcontinent and US, as well as the Indian subcontinent's relationship with Canadian and Australian cuisines is obtained, as you can see here. So these correspond to a value of negative 0.8, and hence a negative relationship is obtained, as I said. So apart from these geographical relationships that we have obtained, some interesting patterns have also been seen. So a closer relationship between Canadian and French cuisines is obtained as compared to the relationship between Canada and US cuisines, despite of their geographical proximity. And we can say that this is owed to the fact that Canada was earlier a French colony. Another interesting grouping is that of the Indian subcontinent and Northern Africa. Furthermore, the Indian subcontinent has also shown a close relationship with Italian cuisine in the authenticity-based clustering tree. And we can say that this is owed to the fact that there is a prevalent use of spices in these regions, and hence we can say that the obtained clusters are able to identify relationships deviating from the geographical similarity. So some of the future works that I have mentioned here are that we need to account for ingredient aliases, as like a brinjal in India is an alias for eggplant in USA. Furthermore, we should also account for complex factors like climate, economy, ingredient state, etc., which would help us in further refining the results. And most of all, I believe that a better validation metric would definitely help the cause. I believe that we need a robust quantifiable validation metric that can also account for all of these complex factors also. So at last, I would like to conclude that in this exploratory work, we have aimed to characterize every cuisine and define relationships between them. Furthermore, we can say that these cuisines, the relationship between these cuisines can also show us some relationship between the people living in these regions and their cultures. So yeah, that's it. Thank you, and I would be glad to answer any of your questions. Thank you.
Thank you so much. I believe there is one question which Bill wrote in the chat box, but I think we will be taking that question in the panel which will happen after this session. So can I now invite our next speaker, who is going to present the paper. This is a short paper, classification of cuisines from sequentially structured recipes. And the speaker is Utkarsh Upadhyay from Jamia Millia Islamia University in India. Do we have the speaker with us?
Yes, sir.
Okay. Okay, Utkarsh, please, in your time.
Okay. Can you see my screen?
We can, yes, thank you.
Okay. Good afternoon and namaste, fellow researchers. I'm Utkarsh Upadhyay here on the behalf of Complex Systems Lab, IIIT, Delhi, to present you the work that we have been doing in our labs. Today, I'm presenting the paper titled Classification of Cuisines from Sequentially Structured Recipes. So, in past, several researches have been conducted in the areas of like recipe generation, recommendation, and even classification. But they all tend to presume that the most dominant feature in a recipe and the most dominant feature or a part of a recipe is generally an ingredient. This fact holds true for majority of the time, but what we are trying in this research is that we are trying to inculcate all the other substructures as well that are present in the recipe, like the utensils, the processes that take part while in a recipe, which these are like very essential parts. Like a recipe is defined by the whole process of like how it's made. So like considering the all the parts starting from getting the ingredients and then preparing the recipe, and then even serving the recipe and using the right utensils to serve the recipe. These might vary from region to region, from like places all around the world. Like it differs. So what we are trying to do is that from our own data set, that is recipe DB, the research that we have done in our lab, we created this data set, and we made sure that the data set is in sequential order, so that when we take the data and when we prepare it, we get a complete sequence of like from the start to the very end of the how a recipe is made. So that's what we have tried to do, and we have tried to make sure that this makes sense, like the whole process of it, the sequences, they account for the results. So the challenges that we faced while carrying out our work was like preparing and pre-processing the dataset, because there were lots of features. There were so many ingredients, there were so many, not so many, but uh, quite a few utensils and processes, and the sequence itself. So we tried to maintain the complete sequence, and we tried to not lose uh, too many features while performing the uh, data engineering. So and do the feature engineering, which included removing the high frequency features and the low frequency features, like the features that occur in around all the recipes, and the features that occur and are very specific to even one recipe. So removing those kind of features and not dropping the classes. So we made a point, and we tried to experiment with this, since the previous researches and the previous works uh, they drop the classes, they drop the regions, and they drop the data, they lose the data to better their accuracies. But we are not trying to get better accuracies, we are just trying to make sense that even sequences matter of a recipe to predict, to do the classification. So those were the few challenges that we faced. Now coming to data set that we use. So we use the recipe DB data set for our analysis. The data set contains around 118,000 recipes across 26 cuisines, across 26 regions. It contains just about 20,000 ingredients, unique ingredients, and 256 unique processes, and 69 unique utensils. We lost a few utensils there, but they are quite a lot to consider. Again, our analysis involves like all the substructures of the recipe. So it involves the ingredients, the processes, and the utensils, all three of them. And because of this, since the processes and utensils are quite a few than the ingredients, there is like huge sparsity in the matrix. Like add occurs too many times, and there are some things like the utensils, they occur a very few times in a very few recipes. So that was quite a challenge. Now a bit look into our data set. We can see I've tried to show different recipe IDs which we have in our data set. So a small visual for our data set which shows kind of the uniqueness and the order, the sequences here that we have. Like in the start we have ingredients, and in the end we have the process and utensils in which it's served, and then we have the features, that the substructures, and the dominant ones, the top three dominant features of each substructure. Like in processes, we had boil, add, and cook too many times. They were all dominant. In ingredients, salt, water, and onion, which makes sense. These three were very dominant across all the recipes. And utensils, pan, bowl, and skillet. Again, very dominant. The methodology was very basic, and since it was a very generic analysis, we started with data cleaning and then vectorization. In vectorization, the data was processed to using the tokenization, TF-IDF vectoring, and the data is further processed to confirm the classification model requirements. So the vectorization preserves the sequences a little bit, not too much. It takes in account of like the weighted dependencies, but does not really depends on it. So then we train, test, and split our data set, and we do the label encoding of all the 26 regions, and then we have two different pre-processing stages for our data set. So in one, we do the pre-processing according to the sequences. So if there is a sequence, then we use our sequence models, and if there's not a sequence, then we use our statistical models. So we presume that we don't have a sequence, and we presume that we have a sequence. So there were two presumptions just simply made. So one of our presumptions says that we have a sequence, and then the preprocessing is done according to it, which involves what to vec, and using the models like LSTM. The LSTM that was used was simple vanilla LSTM with a single layer. And then we used some state-of-the-art NLP models, the transformers, which work on the attention modeling, and autoencoders. So those two were Roberta and BERT. And for the statistical models, we used SVM, logrank, and random forest. So very basic models there, but they perform and they give state-of-the-art results in the NLP tasks. So we decided to go with these models, and we did some hypertuning, and we got the results, which are here. So in the results, we can see in the statistical models, logreg is giving highest accuracy, and it's not really good accuracy for a statistical model or for any analysis. But given the sparsity of our data set, the model was destined to not perform so good. So in the statistical models, logreg performed at like very averagely, and then we tried all the sequence models. Since the LSTM model had only one layer, it performed poorly. But we do expect if we have if we have a better architecture for an LSTM and better computing power, it could yield better results, as it only accounts for a single direction, like it performs the analysis left to right. So it can perform better if the data or the vectors are fed to it in multiple layers. And the transformers, they perform really better than all the other models. And the BERT and Roberta, they gave quite a better accuracies, not very good accuracies, but enough accuracy to justify that there might be a dominance in sequences modeling. And yeah, so because the BERT and Roberta models, the transformers, they are bidirectional. So the word vector, they read the word vectors in both the directions, and transform them using and does the encoding and use the autoencoders, and thus gives the results on the trained data, and hence they obtained a better accuracy. The limitations of LSTMs have been overcome in transformers, as explained, which resulted in an accuracy. of 73% and a loss of 0.10 on recipe DB dataset. On any other dataset which might be a smaller and a better dataset in terms of sparsity, it might perform better. All of these models might perform better, but what we have tried is we have tried to keep the sequence of a recipe intact. So it gives the least errors in across all the models. So that's our basis to determine that this is the best model here. Now the conclusion, we presented a strategy to treat recipes as a chain of events that are similar for a region, but contrasting from other regions to some extent. And this article raised issues that might help in providing another path, a new path to data engineering in food sciences, where researchers take in account the sequences also and other substructures of a recipe also in the AI modeling of a recipe. Coming to future work, this work is not mature enough in terms of results, and these results can be substantially improved. While our analysis considered for sequential nature of recipes, the relationship among all the three substructures have been unaccounted. So what we can possibly do in here is we somehow create a relationship between all the three substructures to better the sequences of our data and thus perform this experiment again, which might yield a better and a different result. And to boost our LSTMs, we can add more layers to the LSTMs, and we can use the word vectors from the BERT and Roberta models and feed it to our LSTMs so that a better accuracy and a lower loss can be produced. And a bit more better feature engineering can be done to reduce the sparsity in the dataset so that even our statistical models improve a bit. And using just all the three substructures of the recipe in every other aspect that is there in food data engineering. That's it. I'll be happy to answer any question related to the article that I've just presented. Thank you.
Yes, thank you so much. So I believe this brings us to the end of this session. Any questions will be answered in the panel session, which will follow after the coffee break. So I believe that the coffee break will last just over half an hour. So please also don't forget to vote for the Best Paper Award. You have the Google link on the screen right now, and we are going to return at 3:30 Texas time, which is around 38 minutes from now. Thank you very much for attending so far, and we look forward to rejoining you in just over half an hour's time.
Can somebody put that link up on the chat? I guess I can.
Yeah.
Let's see.
Bill, somebody has done it already.
Oh,
So,
okay.
yeah, so it's done. Thanks a lot.
Okay.
Yeah. So great. Okay, so I'm just gonna go out for another around 20 minutes or so, and I'll see you all very, very soon thereafter. Okay.
Okay. Consequel. Hello?
Hi, William. This is
Yes.
John called Chronicles, the magazine. How are you today?
Oh, fine. Excuse me, I gotta.
Today our call is.
Can you hold on just
Go
a
ahead.
minute? I'm in a virtual
Yes, absolutely.
in a virtual conference, and I have to shut my mic off.